In this recording, we're going to talk about blood flow through the heart. But before we do that, I'm just going to go back a little bit and review the cardiac cycle. Okay, so we have 4 chambers. And one heartbeat consists of 2 phases. So the atria contract together, and then the ventricles contract together. And that makes up one cardiac cycle. Whenever a chamber is relaxed, we call that diastole. Okay, and when a chamber is relaxed, it's filling. And when a chamber is contracting, we call that systole, and that chamber is ejecting blood. And the heart contracts in a 2-step pumping action. So the atria contract together at the same time. When they contract, they squeeze, which sends blood into the ventricles. The ventricles fill. There's about a 0.1 second delay, and then the ventricles contract together. And when the ventricles contract, they eject their blood. So the right ventricle ejects its blood into the pulmonary vein, and the left ventricle ejects its blood into the aorta. So the 2 phases of the cardiac cycle are usually described based on what's going on with the ventricles. So you've got the ventricular relaxation phase. So the first phase, during the first phase, the ventricles are at rest, and therefore we call that ventricular diastole. And while they are at rest, they are filling with blood. Simultaneously, while the ventricles are at rest, the atria are contracting. So the atria are in systole while the ventricles are in diastole. And when the atria are contracting, they're ejecting blood, and that blood is going into the ventricles. So the filling that we're talking about here is the filling that is coming from the atria into the ventricles. Okay? So the atria are contracting and ejecting their blood into the ventricles. The ventricles are relaxed and they are filling with blood. This represents 2/3 of the cardiac cycle. And I'll come back to that in a second. The second phase is ventricular contraction. So the ventricles are now in systole. So the ventricles are contracting. When the ventricles contract, they eject their blood. And as I said before, the right ventricle ejects its blood into the pulmonary vein, and the left ventricle ejects its blood into the aorta. So ventricles are contracting and ejecting blood. Simultaneously, okay, so now we've got the reverse, the atria are in diastole. The atria are relaxed, and now they're refilling with blood. Okay, and their blood comes from, the blood going into the right atria is coming from the vena cava, and the blood going into the left atria is coming from the pulmonary artery, bringing fresh blood back from the lungs. And the ventricular contraction phase represents 1/3 of the cardiac cycle. So let me show you what that means. So every time the heart beats, we get atrial contraction, ventricular contraction. That makes up one cardiac cycle. If your heart is beating 75 beats per minute, each cardiac cycle takes 0.8 seconds. Okay? And of that 0.8 seconds, 0.3 seconds are spent in ventricular systole, and 0.5 seconds are spent in ventricular diastole. Therefore, at rest, 2/3 of the cardiac cycle consists of the ventricles being at rest, and therefore the other third is the ventricles contracting. Okay, so 2/3 of the time the atria are working, 1/3 of the time the atria are relaxing. Vice versa for the ventricles. This 1/3, 2/3 number is only true at rest. So if we look at an extreme situation, very heavy exercise, 180 beats per minute, if you're going to have 180 contractions in a minute, your cardiac cycle is going to have to happen much quicker. Okay, and what we see is rather than each cardiac cycle lasting 0.8 seconds, we get a cardiac cycle of 0.33 seconds. So a much quicker cardiac cycle. And what we see is the proportions also change. So during exercise, the majority of the cardiac cycle is spent with ventricular systole, and a small portion is spent with ventricular diastole. So basically at rest, most of the time, 2/3 of the cardiac cycle, the ventricles are at rest. But during exercise, because the ventricles have to do significantly more work in a shorter period of time, most of the cardiac cycle is spent with ventricular systole. Now we're going to talk about blood flow through the heart. We've got our 4 chambers again. We've already established in a previous recording that the driving force for blood flow is a pressure gradient. And blood will always flow from an area of high pressure to an area of low pressure. So let's track the pressure changes that drive blood flow through the heart. So we're going to begin with the atria relaxed. Okay, and when the atria are relaxed, the pressure in the atria is low. There's also pressure in the vena cava and pressure in the pulmonary artery. When, as I said, the pressure in the atria is very low when they're relaxed, and this sets up a natural pressure gradient. Okay. So P1, P2. Okay. P2 is the pressure in the atria, which is very low when the atria are relaxed. And this sets up a natural pressure gradient such that the pressure in the vena cava and the pressure in the veins, pulmonary vein, is higher than the pressure in the atria. So P1 is greater than P2. Therefore, blood is going to flow from P1 to P2. Okay, so this is why blood flows from the vena cava into the right atrium and from the pulmonary artery into the left atrium. Okay, and we call this flow passive. It's a natural pressure gradient that exists when the atria are relaxed. And we'll talk in a little bit about what active means, and that'll help you understand better what passive means. So blood is flowing into the atria. As blood flows into the atria, okay, the atria fill with blood. As the atria fill with blood, the atrial pressure rises, okay, because that blood is putting pressure on the walls of the atria. And so P2 starts to rise. Eventually, as P2 rises, okay, remember that we started with P2 less than P1. And as P2 rises, eventually P1 and P2 will be equal. When P1 and P2 are equal, we call that equilibrium. And therefore there's no pressure gradient. If there's no pressure gradient, there's no driving force for blood flow, blood stops flowing. Okay, so we had a pressure gradient, caused blood to flow from the vena cava to the right atrium, the pulmonary artery to the left atrium. As the blood flowed into the atria, the pressure rose. Once the pressure got up high enough that it was equal to P1, we ended up with equilibrium. Blood stopped flowing. That's how the atria fill. Now let's talk about blood flow into the ventricles. So now we're talking about a different pressure gradient. So now we have P1 here and P2 here. And we have these valves. So as the atria were filling, the pressure in the atria was rising, and at the end of filling, atrial pressure is greater than ventricular pressure. Okay. Remember that as the atria, let's just keep it there. Eventually the pressure in the atria is greater than the pressure in the ventricles, and this is because of the pressure that rose in the atria as they were filling with blood. This sets up a pressure gradient between the atria and the ventricles. And because the pressure is higher in the atria than in the ventricles, what we get is blood flow from both atria to both ventricles. Okay? And again, this is a passive pressure gradient. This is a natural gradient that occurred because of the filling of the atria. Okay? Now, as blood flows from the atria to the ventricles, the pressure in the atria is going to drop. Okay, so as the atria lose blood, there's less and less pressure on the walls of the atria, so the pressure in the atria is going to drop. Simultaneously, as the ventricles fill, now we've got pressure on the ventricle walls, and the ventricular pressure is going to rise. Eventually, as before, P1 is going to equal P2, okay? Because P1 is dropping, P2 is rising. Eventually, P1 equals P2. Again, we have equilibrium, no more pressure gradient, and therefore no more blood flow. Now, this is responsible for 70% of the blood flow out of the atria and into the ventricles. But we still have 30% of the blood in the atria that we need to get to the ventricles. So that's the next step. So the next step is what we call atrial kick or atrial contraction. So now the atria contract. Okay. So remember, we have rising pressure in the left ventricle, rising pressure in the ventricles, dropping pressure in the atria. Atrial and ventricular pressure are eventually equal, and at this point 70% of the blood in the atria has been moved into the ventricles. We have another 30% that we need to move, but we don't have a pressure gradient, so we have to create a pressure gradient. So what happens here is that the atria contract. When the atria contract, they squeeze. And when the chambers squeeze, the pressure rises in the chambers. Okay? Remember that right before this, P1 and P2 are equal. So atrial pressure is now rising. That's P1. So again, we have a pressure gradient where the pressure in the atria is greater than the pressure in the ventricles, and this is going to allow additional blood flow from the atria to the ventricles. This time, the pressure gradient was active. Okay, and what active means was that we had to use some energy to create a pressure gradient. Okay, and that energy was used to cause the atria to contract. So prior to this, all the blood flow occurred without the need for any type of contraction. But we had to get that additional 30% of blood out of the atria into the ventricles, so the atria contract. When they contract, they squeeze. When they squeeze, the pressure in the atria rises, creates a gradient such that more blood, an additional 30%, is going to go from the atria to the ventricles. At this point in time, and eventually, again, that flow is going to occur until P1 equals P2. So eventually you reach equilibrium, no more blood flows out of the atria. The next thing that happens is that the ventricles contract. When the ventricles contract, they squeeze, just like the atria did. When they squeeze, the pressure in the ventricle rises. So we get an increase in pressure in the ventricle, which, because we had equilibrium between the ventricles and the atria, if the pressure in the ventricles rises, this is going to set up a gradient such that the pressure in the ventricles is higher than the pressure in the atria. But blood will not flow backwards. Okay, even though the gradient is going to favor blood flowing from the ventricles to the atria, this is not going to happen because these valves are one-way valves that only allow blood to flow in one direction, and blood is not allowed to flow backwards. So as the pressure in the ventricles rise, we get a pressure gradient between the ventricle, the right ventricle, and the left ventricle, so what we get here is the new P1 is ventricles. P1 is always the higher of the two pressures. The new P2 is the pressure in the pulmonary artery, the pressure in the aorta. And so as the pressure in the ventricles rises, ventricular pressure is eventually greater than the pressure in the pulmonary artery, the pressure in the aorta. This is going to cause blood to flow from the right the right ventricle to the pulmonary artery, and from the left ventricle to the aorta. Okay. And because this gradient had to be created with contraction, this was an active gradient. This blood flow was active. It required contraction. It required the use of ATP in order to create the gradient such that ventricular pressure is greater than the pressure in the pulmonary artery and the aorta, and therefore blood flows out of the ventricles. And again, as blood is leaving the ventricles, the pressure in the ventricles is going to drop. Okay? And as the pressure is dropping, P1 is dropping, eventually, again, P1 is going to equal P2. Okay, so eventually the pressure in the ventricles is going to be the same as the pressure in the pulmonary artery, the pressure in the aorta, and therefore once equilibrium is achieved, blood flow stops. And the ventricles have now completed their ejection of blood.